The next speaker we have is Nate Brown. He's going to talk to you about Immunology, Kubernetes admission controller. Hope you all have a great talk.
Hey everybody, my name's Nate Brown. I'm a web systems engineer at Farm Credit Service America on our platform engineering team. Outside of work, I'm the proud owner of visitreadonlyfriday.com. I'm also a marching band visual technician, which just means I do marching band stuff for the local area high schools. And my philosophy is, while I might not be on the security team, I think security is everybody's job. So I help them out, I do whatever. Additionally, I also run multiple production Kubernetes clusters with admission controllers, so I like to think I know what I'm talking about. So what are we here for? We're here to learn about admission controllers in Kubernetes. We'll learn about the types, the phases, configuration, some use cases, and we'll see how these work with PSPs and PSAs. We'll also learn about some easy-to-use admission controllers and see just how quick you can get started using them in your clusters. So, what is Kubernetes? For those of you who don't know, basically it just orchestrates pods. You can think of pods as collections of containers similar to cells. And containers are just like mitochondria. They're the organelles within pods. They're the powerhouse, if you will, of pods. So some pods are blood cells, which are good. Other ones are bacteria, which are bad. And there's other objects in Kubernetes, but we don't really care about those ones today. So imagine, if you will, this is a wild Kubernetes cluster. Like our bodies, our clusters have valuable resources that hackers want access to. It's a constant fight against pathogens in our bodies and a fight against YAML in our clusters. Our bodies have to fight a child's sneeze, whereas our cluster has to fight that hacker's YAML. And you might be thinking, well, I have role-based access control. Surely I'm good. Well, not so. Imagine a scenario where a cluster is taking a walk in the woods, when suddenly it steps onto a random pod spec. It's kind of like touching a gross doorknob for Kubernetes. Just like our skin is a barrier, so too is authentication and authorization, and barriers can be overcome. Our skin can be cut and our authentication tokens can be stolen. Additionally, Kubernetes RBAC can't really stop a root container with a host path mount. So we need some defenses for our defenses. In our body, we have skin. It blocks intruders. We also have our dendritic cells, which inspect intruders. In Kubernetes, we have RBAC and authentication, which blocks intruders. And we have admission controllers, which can inspect. When you get cut, your cells release chemical signals that invoke the immune system. And similarly, when a user makes an API request to create or modify an object, admission controllers are invoked. So you might be wondering, what are admission controllers? Well, they're kind of like immune cells in the fact that there's actually a lot of them. So let's put them under the microscope. So, admission controllers, they're compiled directly into the API server. They're kind of like the cell's DNA. They're invoked after authentication and authorization, but before they're actually persisted. There's two different types. We have the mutation, which they can actually mutate the objects users submit. And we have validation, which just validate what users submit. They can also be both. And really, all that typing does is it just determines in what phase they're ran in and what they do. So let's look at the phases of admission. It's a two-step process. In the first phase, our mutation admission controllers run sequentially. Loops can occur in special scenarios, and we'll talk about those later. In the second phase, all of our validation admission controllers run simultaneously. It's important to note, if any admission controller at any point in the process rejects it, you're done. It's one strike and you're out. Other controllers don't actually get told about that failure. So if you are using admission controllers or you're writing your own, it's important to know, even if you accept it, others might not. So let's look at some example controllers. The first one we have is the always pull image controller. It's a mutating controller, which means it can actually modify the objects users submit. So if somebody submits a pod and they say the image pull policy isn't always, it actually takes that object, modifies it to say always, and then persists that to the data store. On the other hand, we have the namespace exist admission controller. It's a validating admission controller. It looks at the namespace that's specified, make sure it exists. If it does, it accepts it. If it doesn't, it'll reject it. So, writing code. There's a limited number of admission controllers built in, and you have to remember they are actually compiled directly into the API server. So you might be thinking, that's a lot of code I'm gonna have to write, and I'm also gonna have to maintain my own API server builds, my own infrastructure, I'm gonna have to do patching. You're probably thinking, there has to be a better way. And there is. I'd like to introduce two special admission controllers. The first one is called the mutating webhook admission controller. The second one is called the validation webhook admission controller. These use webhooks that are invoked to inspect the incoming YAML. Technically it's JSON, but I like YAML. And similar to a lymphatic system carrying messages across our bodies, these use HTTP callbacks to carry messages between the API server and the emission controller. They're configured via mutating webhook configuration and a validating webhook configuration object, respectively. You can think of these as RNA for these special emission controllers. So what's configurable? You define a list of webhooks. These webhooks are invoked anytime a request comes in if they follow certain rules. These endpoints that are called, they can be internal to your cluster, or they can be external services. So if you have a security product outside of your cluster that offers emission controllers, you can use it if you want. We also have the rules. Those specify the specific API groups, the operations, etc. This is how you can target specific pods versus something like a deployment, or whatever you want. We also have selectors, which are just labels. So you could say, I only act on pods that have the department equal to finance. You can enforce certain controls depending on those arbitrary labels. We also have the reinvocation policy, which is exclusive to mutating emission controllers. Remember earlier how I said they can loop in special scenarios? This is it. This just says, hey, if somebody else modifies the object, you should reinvoke me so I can do something additional. So you might be wondering, what actually gets posted to the webhook when it gets called? It gets an emission review object. They're posted as JSON, but I like YAML again, so we'll see YAML on the right. The first thing is a UID. We also get the object kind of what it is. We get the identity, the namespace, the operation that's happening. We also have the information about the user submitting the object. You could re-implement RBAC here if you really wanted to. At my work, we actually do. If you want to know more about that, come find me and talk to me. And we actually get the object itself. On deletes, obviously it's null. On updates, we get the old object and the new object. And on creates, we just get the object. You can inspect these and do whatever you want with them. So, what actually gets returned? What do we, as a webhook, return to the Kubernetes API server? We also respond with an emission review object, ironically. In terms of HTTP parlance, you must respond with a 200 regardless of what choice you make. The denial info actually goes in the body of the request. The UID defines how the API server tracks requests. And you might be thinking, this all sounds well and good, but I've heard about this thing called pod security policies in my cluster. Why do I need emission controllers if I have those? Well, in my opinion, pod security policies, they're limited in their functionality. And if you're running newer Kubernetes versions, so is the pod security for pod security emission. Those are targeted just at a pod level, and emission controllers can go deeper than that. But really, consider them just as another immune cell that your cluster has. If you can use both emission controllers and PSPs or PSA, you should do it. There's no reason not to have a defense in-depth approach. And you might say, hey, cool story. What can I, as a professional, actually use these emission controllers for? And there's a lot of things. You can limit which container images are allowed. You could also validate that they're signed. You could enforce certain AppArm or SE Linux settings on the containers within pods. You could prevent users from creating wildcard virtual services or ingresses. That way they can't man in the middle of each other. You could tie into a CVE scanning tool. If you have a tool, you could call it and see, hey, does this container image have too many CVEs? If it does, you can block it. You could also enforce operational policies. If you had like an asset control system that does change management, you could make sure any object being submitted to your production clusters has a corresponding change record. And you might be thinking, that's a lot of web services that I will have to make. I don't really want to write code. I'm not in the business of writing webhooks and all that stuff. And the good news is, you don't have to write code. There are a lot of low-code and low configuration options out there. So some no-code examples are NuVector. There's also Sysdig. And some low-code options are OPA Gatekeeper. They use the language called Rego. And there's also Keyboarded by SUSE. And it uses pretty much any language you want, as long as it compiles down into WebAssembly. Where I work at Farm Services America, we use NuVector and OPA Gatekeeper, so I'm the most familiar with those two. So let's do a little in-depth look at those two. NuVector, like I said, it's a no-code option. It's actually a full runtime security product. It has scanning components, which is why we like it, which means we can have CVE-based policies. It also has some file compliance checks for like making sure you don't have raw API keys in there, you don't have certain private keys, et cetera, et cetera. They were recently acquired by SUSE, and they've been open sourced. So that means you can run it in your cluster without talking to any salespeople. You don't technically need a license or anything like that. You can just run it. And it's actually super easy to install. So with that, let's get into a demo of installing. So first, we add it to the Helm repo. If you've never used Helm, it's just a package manager for Kubernetes, similar to Yum. Then we create a namespace for new vector to live in. We then do a helm install new vector. We set some options, whatever. And I'll fast forward here real quick, just through the pods coming up. I'll get the service port. Open up a web browser, go to that node port service, and we'll see the new vector UI comes in up. Just log in with the default credentials, admin. Say, yes, I've read the license agreement, smash that login button. Then you'll get the UI. You just come to policies on the left-hand side. You click admission control. You turn them on. You click add. And in here, you can add pretty much any policy you want, almost. So in this example, I'll just make a policy that doesn't allow root pods. So I'll say, hey, no root pods allowed. And in this criteria, you can see there's a lot of different options. Anything from CVE count, like I mentioned, certain environment variables, the image, labels, mounts, PSP best practices, the user it runs as, et cetera, et cetera. For this example, I'll just click run as root. I'll add that criteria. I'll click add. And then instantly, without 10 minutes of work, I have an admission controller in my cluster that doesn't let people run root pod. Another one we use is OPA Gatekeeper. It's kind of like a T-cell in the fact that it has a memory. So you can have certain policies happen if certain other objects have been created or not. It's capable of both validating things as well as mutating objects. They use a language called Rego for their implementation logic, but don't let that scare you. They have a super excellent community, and similar to New Vector, it's a Helm-based installed. The thing I really like about it is that it has auditing and dry run modes. This means you can actually write your policies and audit your cluster. You can also have dry run modes, which mean, hey, notify me about violations and warn my development teams before you actually block it. It's great for when you introduce new security standards that have an in-effect date that's not today. Again, don't let the Rego scare you. On GitHub, there's a super great Gatekeeper library. It's got general policies and any PSP replacement policies for those of you updating your Kubernetes clusters. And it's regularly updated. It's not something that they just put out there and they forget about it. For example, when ephemeral containers were added to the API spec, within the next day, OPA had them. So it's super great, super easy to use, even if you don't want to do Rego. But again, Rego isn't actually that hard, I promise. So in summary, we learned admission controllers act like a second line of defense in our cluster. They're similar to our immune system in that they inspect intruders and validate that they follow certain rules in our bodies. Admission controllers can also implement our organizational policies in addition to security and technical ones. And there's a lot of great out-of-the-box admission controllers you could use in your cluster today. If you're not using them, seriously, look at them. They're super easy to use. It literally takes 10 minutes to get started. And with all of them, they have dry run modes, so you don't have to enforce clusters. You can audit your production clusters. They're super easy to use. So for some further reading, I know you guys probably can't click on these, but I'll post these to my Twitter. Take pictures if you want any of these. Yeah, and if you have any questions, let me know. My website is visitreadonlyfriday.com. You can see my Twitter handle there, my email. Come find me. I love talking about Kubernetes. I'll talk your ear off about our policies. I'll tell you about that RBAC thing, how we re-implemented RBAC. Not really, but kind of. And you can see my co-author there. So, any questions? Yeah, so the really nice thing in OPA particularly, you can actually specify what message they get back. So we have policies that say you can't run a specific SHA-based image. And so you can actually customize it to say, hey, you're using this SHA or your base image, you should use this one instead. So it's completely customizable, and we like it because our developers don't have to come bug us about it. Go for it. Ooh, what does it not do? I can't really think of anything, just because at a root level, the way Kubernetes objects are configured, anything you can configure or change, OPA can inspect and change and do and deny. It's kind of like a human eyeball in a way. So anything you can do, it can block. Anything else? That's a great question. I'd say probably about 70% of our policies are just pulled straight from the Rego library. We have like our other 30 that we've just written ourselves by taking existing Rego policies, seeing how they work, and just modifying them. Rego Playground, it's a great resource if you want to get into writing Rego. It's super easy, super low maintenance if you want it to be, but again, as the threat landscape changes, you can adapt with it, or you can just rely on the open policy library. Anything else? Perfect. Thank you very much, everybody.